Okay, so this problem is asking about an electron beam which is inside an old television picture tube that's 0.40 millimeters in diameter and carries a current of 50 microamperes. The electron beam impinges on the inside of the picture tube screen. So a picture isn't going to be incredibly important in order to set this problem up, but it can be helpful to kind of visualize what's happening. So essentially we have this tube that a current is going through, and that electron beam is going to create that picture on the screen. Part 1 is asking us how many electrons strike the screen each second. So for this, we're going to use our definition of what current is, which is some magnitude of charge over time, which can be simplified to the charge of one electron by the number of electrons that's hitting it. And since we know the time that we're going to be using here is 1 second, we have all we need to know with all those variables. So rearranging for number of electrons and plugging in our given numbers, notably always making sure to convert our units to the correct value, we get a value of 3.1 times 10 to the 14th electrons. For the number of electrons for part A. So part B is asking what is the current density in the electron beam, and current density is defined as current over A, and that A is the cross-sectional area. So for our tube, for example, you can see that area is going to be that circle using that diameter value we were given. So the first thing that I did was just solve for that area. And I ended up getting a value of 1.6 times 10 to the negative 7 meters squared, and then just dividing that by our current value we were given, we get a total current density of 400 amperes per meters squared. So that's part B. Part C asks, the electrons move with a velocity of 3.8 times 10 to the 7th meters per second. What electric field strength is needed to accelerate electrons from rest to this velocity in a distance of 5 millimeters? So we were given some new information, which is obviously those velocities and the distance, but we're trying to solve for electric fields. So the key thing here is just finding equations that contain all of that information. So what I did was I set up a force thing, which states that that electric force is charge times the electric field. So it's going to be the charge of the electrons times the electric field, and obviously we have to account for how many of them there are. So that's why that number of electrons is in there. And then you can equate that to essentially the F equals ma equation. But the way I've written it shows the number of electrons times the mass of an electron times the acceleration. What we can immediately see from these equations, though, is that NE will cancel. So just keeping that in mind as we go forward. So in order to plug in what are values that we have in the problem for A, I used one of the kinematics equations, and then solved for A, which you can see below, and got that A equals velocity squared over 2 change x. And so we can go ahead and plug that into that equation and rearrange for E. So once you do all that, you get a final equation of E equals mv squared over q 2 change x. So we have all of those values. The really key thing to not mess up here is, once again, just making sure that you convert your units correctly. But if you do that and plug everything in, you get a total of 8.2 times 10 to the 5th volts per meter. So our final part is asking, each electron transfers its kinetic energy to the picture tube screen upon impact. What is the power delivered to the screen by the electron beam? So not to be confused with electric field, our power equals energy over time, which can be represented by like the 1/2 mv squared equation, but you can see the way I've converted that is accounting for how many electrons are going to be involved in the interaction. So you can see that we're going to have to multiply that top part of the equation by the number of electrons. And then our time is just going to be 1 second. So once again, this is as simple as just plugging things in because we know all of these values, velocity from the previous part, and so on. And when you plug everything in, you get a total power delivered to the screen by the electron beam of 0.204 watts. So that's the end of the problem. I think the tricky thing about this entire equation is keeping up with your values and what you know. It also uses a lot of equations from past units, so it's good to always have some sort of equation sheet there or just have a good memory with these. Because some of these equations, like I said, it's been a little bit since we've used them, but overall it's not too bad. Thank you for listening.